The DevOps Revolution, Transforming Software Delivery from Code to Customer. Chapter 1, The Code to Customer Conundrum, Why DevOps Matters. In our modern world, invisible lines of digital code power almost everything we do. From waking up to the alarm on our smartphone to ordering coffee, commuting to work, connecting with loved ones across continents, and managing our finances, software is the silent engine of daily life. We've come to expect these digital services to be fast, flawless, and always available. When an app crashes, a website loads slowly, or a service experiences an outage, even for a few minutes, our perfectly curated digital world can feel like it's grinding to a halt. Yet behind the seamless user experience, the reality of creating and delivering this software can often be anything but flawless. For those working within the software industry, it frequently means slow, painful releases, a constant battle against unexpected bugs, and perpetual firefighting. Teams can find themselves trapped in a blame game, pointing fingers across organizational divides, while deadlines loom and customer satisfaction dwindles. This raises a fundamental question. In an era of unprecedented technological advancement, why is software delivery still so hard? Why does it often feel like a continuous uphill battle from an initial idea to a working product in the hands of a customer? This book aims to answer that question and, more importantly, introduce you to a powerful philosophy and set of practices known as DevOps, which offers a blueprint for building and running software with greater speed, reliability, and harmony. The Wall of Confusion, A Tale of Two Teams. To understand why DevOps became necessary, we need to look at how software development organizations traditionally operated. Historically, there existed a significant, often invisible, chasm between two critical groups within any technology company: the development team and the operations team. This divide became so pronounced that it was often metaphorically referred to as the Wall of Confusion. On one side of the wall stood development, or dev. These individuals were the architects and builders of the digital world. Their focus was firmly on innovation, creating new features, fixing bugs, and writing fresh lines of code. They were driven by the need to deliver new capabilities to customers as quickly as possible, to out-innovate competitors, and to continuously improve the product. Think of them as the brilliant chefs in a bustling restaurant. Their passion is creating exquisite new dishes, experimenting with flavors, and surprising diners with culinary artistry. They thrive on creativity and rapid iteration, constantly pushing the boundaries of what's possible with code. On the other side of the wall was operations, or ops. These were the guardians of stability, the caretakers of the digital infrastructure. Their primary responsibilities included keeping the servers running, ensuring the network was stable, and making sure the software was accessible and performing reliably for customers 24 hours a day, 7 days a week. Their world was about uptime, security, and minimizing risk. To extend our restaurant analogy, ops are the meticulous restaurant managers. Their job is to ensure the kitchen runs smoothly, the refrigeration is working, the dining room is spotless, and everything is in perfect order so patrons can enjoy their meal without interruption. They prioritize consistency, reliability, and predictability. The inevitable clash arose from these differing goals and incentives. Dev teams wanted to ship new features frequently, even if it meant introducing changes that might slightly disrupt the stable environment. Ops teams, conversely, wanted stability above all else, seeing every new piece of code as a potential source of disruption or failure. Dev would often throw the code over the wall to ops, expecting them to magically deploy and maintain it, often with limited documentation or understanding of the operational needs. Imagine the chef suddenly presenting a complex, never-before-made dish to the restaurant manager moments before a busy dinner service, expecting them to immediately source strange ingredients, recalibrate the ovens, and train the serving staff, all without disrupting the ongoing flow. The manager, focused on ensuring smooth service, would naturally push back, arguing for consistency and a more controlled introduction of new items. This scenario played out constantly in the tech world. The result was high stress, low trust, and painfully slow processes. Developers grew frustrated by the perceived lack of agility from operations, while operations teams felt constantly overwhelmed and blamed for problems caused by code they hadn't been adequately prepared for. This wall of confusion crippled organizations, preventing them from realizing the full potential of their software and their talented people. The business impact of software delivery bottlenecks. The friction between development and operations wasn't just an internal problem. It had profound and damaging consequences for the entire business. Firstly, there was slow time to market. In today's fast-paced digital economy, the ability to innovate quickly and get new features into customers' hands can be the difference between leading the market and becoming obsolete. Organizations burdened by the DevOps divide simply couldn't keep up, losing critical competitive advantages to more agile rivals. Secondly, there was high deployment risk. Because releases were infrequent and involved large chunks of change, they became inherently risky. The fear of breaking production, of causing a costly outage, led to a cautious, almost paralyzed approach. This often meant extensive manual checks, prolonged testing cycles, and big bang releases that were terrifying to execute and frequently led to unforeseen problems. This, in turn, directly impacted poor quality and customer dissatisfaction. If releases were risky and slow, and changes were not integrated smoothly, the software inevitably suffered from bugs, performance issues, and unexpected downtime. Frustrated customers would then take their business elsewhere. Internally, the human cost was immense. Constant firefighting, blame, and a lack of smooth processes led to employee burnout and attrition. Talented individuals, passionate about creating, found themselves trapped in a cycle of frustration and ultimately sought more fulfilling environments. Finally, the cumulative effect was missed opportunities. When an organization spends all its energy on fixing problems and managing internal conflicts, it loses the capacity to innovate, experiment, and respond swiftly to new market opportunities or competitive threats. It becomes reactive instead of proactive, a glimmer of hope, the need for change. By the early 2000s, it became clear that the problems weren't just isolated incidents or individual failures. They were systemic, inherent in the traditional organizational structures and processes. A realization began to dawn: what if dev and ops didn't fight each other? What if they worked together, not just cooperatively, but as truly integrated partners, sharing goals, tools, and responsibilities? This emerging idea, one of holistic transformation, lay the groundwork for what would become known as DevOps. It promised a way to dissolve the wall of confusion brick by brick, replacing it with bridges of collaboration and shared understanding. It sought to re-engineer the entire process of software delivery, from the initial line of code written by a developer to the reliable operation of that code in the hands of a customer. What readers will gain from this book? This book is your guide to understanding this transformative movement. Throughout the following chapters, you will gain a clear understanding of the why behind the DevOps movement, not just what it is, but why it has become an indispensable approach for any organization seeking to thrive in the digital age. Insights into strategies for transforming your own organizations, teams, or even your individual role. Whether you're a developer, an operations specialist, a manager, or a business leader, you'll discover how DevOps principles apply to your world. A practical roadmap to faster, safer, and more reliable software delivery. A journey towards a more collaborative culture, efficient processes, and effective use of technology. This journey begins with a look back at where software development has been, to truly appreciate how far it has come, and why DevOps represents such a crucial evolution. Let's delve into the history that set the stage for this revolution. Chapter 2: A brief history of software delivery, from waterfall to agile. To fully grasp the significance of DevOps, we first need to understand the landscape it emerged from. Like any innovation, DevOps did not appear in a vacuum. It stands upon the shoulders of earlier methodologies, borrowing their strengths and compensating for their weaknesses. By revisiting the evolution of software development, we can better appreciate how the persistent challenges led to the eventual breakthrough that is DevOps. The grand plan approach. Waterfall methodology. In the early days of computing, the way software was built drew heavily from more established engineering disciplines, particularly civil engineering and manufacturing. This gave rise to the waterfall methodology, perhaps the most intuitive, yet often problematic, approach to software development. Imagine building a bridge. You wouldn't pour the concrete for the deck before you finish the pylons and cables, would you? The process is inherently sequential, with each step forming a prerequisite for the next. Waterfall applied this logic to software, breaking down the development process into distinct, linear phases. Requirements. First, gather all possible requirements from stakeholders and users. Catalog every desired feature, function, and constraint. This phase aims for a complete understanding of what needs to be built. Design. Based on the detailed requirements, architects and designers would then craft a comprehensive blueprint for the software. This included system architecture, database designs, user interface mockups, and technology choices. Implementation, coding. Only once the design was fully approved would developers begin writing code. Their job was to translate the design specifications into working software. Verification, testing. After coding was complete, the software would undergo extensive testing to ensure it met the initial requirements and was free of defects. Maintenance. Finally, after successful deployment, the software would enter a maintenance phase, addressing bugs and making minor enhancements. The perceived benefits of Waterfall were rooted in its structure. It promised predictability, extensive documentation, and clear roles for everyone involved. Project managers loved the idea of a fixed plan, distinct milestones, and a clear path from start to finish. It seemed ideal for large, complex projects where clarity and control were paramount. However, as software projects grew in complexity and the pace of business accelerated, Waterfall's inherent flaws became glaringly apparent. The core problem was its rigidity. In software, unlike building a physical bridge, requirements often change. Users might not know exactly what they want until they see a working version. New technologies might emerge, or market conditions might shift. In Waterfall, changing requirements in a later phase was incredibly difficult and costly, like trying to redesign a bridge mid-construction. It often meant going all the way back to the drawing board. Another major flaw was late feedback. Problems, whether design flaws or coding errors, usually weren't discovered until the testing phase, sometimes months or even years after the initial requirements were gathered. By then, fixing them was immensely expensive and time-consuming, leading to delayed releases and frustrated stakeholders. It was akin to building a house and only showing the owner sketches and blueprints, then presenting them with the finished structure, hoping they like it and that it meets their needs. Any dissatisfaction would involve tearing down significant parts of the house. This Big Bang approach to releases, where the entire software product was built and deployed in one massive, infrequent launch, inherently carried high risk. If something went wrong, the entire launch could fail, often with catastrophic consequences for the business. The rise of agility, responding to change. The limitations of Waterfall led to a growing dissatisfaction within the software community. Developers and project managers yearned for a more flexible, responsive approach that could adapt to changing needs and deliver value more continuously. This desire coalesced in 2001 with the publication of the Agile Manifesto. The Agile Manifesto was a declaration of values and principles by a group of 17 independent-minded software practitioners. It didn't prescribe a rigid methodology, but rather a set of guidelines to foster a different mindset. Individuals and interactions over processes and tools. Working software over comprehensive documentation. Customer collaboration over contract negotiation. Responding to change over following a plan. This manifesto shifted the emphasis from planning and documentation to early and continuous delivery of working software, with a strong focus on customer collaboration and adapting to change. It championed iterative development, where software is built in small, manageable chunks, each delivering a working, testable piece of functionality. Numerous Agile practices emerged from these principles, each with its own flavor. Scrum. Perhaps the most popular Agile framework, Scrum introduced concepts like sprints, short, fixed-length periods, typically 1 to 4 weeks, during which a team completes a set amount of work, daily stand-ups, quick team meetings to synchronize progress, and product backlogs, a prioritized list of features. Kanban, focused on visualizing workflow, limiting work in progress, WIP, to prevent bottlenecks and continuously improving flow efficiency. Extreme programming, XP, emphasized technical practices like pair programming, test-driven development, and continuous integration, a concept we'll explore shortly. Agile's impact was undeniable. It brought faster feedback loops, allowing developers to learn from customer input far earlier. This led to better customer alignment, as the software evolved based on real-world usage. It also significantly improved team morale, fostering a sense of shared accomplishment and autonomy. Agile's unfinished business, the operations gap. While Agile revolutionized how software was developed, it largely neglected the question of how that software was delivered and operated. Agile's focus was primarily on the dev side, getting features built and tested within the development team rapidly. The ops side, however, remained largely untouched by the Agile revolution. Even if developers were frantically building and iterating in 2-week sprints, the traditional operational processes for deploying that software to live systems, ensuring its stability, and monitoring its performance often remained slow, manual, and prone to error. Imagine that Agile restaurant now producing a new menu item every 2 weeks. The chef is thrilled, the kitchen staff is buzzing with creativity. But the restaurant manager ops is still on the same schedule, only changing the entire menu once a quarter. Suddenly, the kitchen has shelves full of new, unservable dishes, creating a new bottleneck. The joy of rapid creation quickly turned into the frustration of delayed delivery. This created a palpable friction. Dev teams, empowered by Agile to move quickly, were constantly pushing for new releases, new environments, and new configurations. Ops teams, focused on stability and minimizing risk in complex, often manually managed environments, found themselves overwhelmed and struggling to keep up. They became the new bottleneck, the gatekeepers. The growing divergence between rapid development and slow, cautious operations highlighted a critical truth. While Agile had brought incredible speed to the creation of software, it hadn't solved the end-to-end problem of getting that software from concept to a consistently working, reliable product in the hands of the end user. The stage was set for a new evolution, one that would bridge this remaining gap and unite the entire software delivery pipeline. This was the precise moment for the emergence of DevOps. Chapter 3: The Birth of DevOps. Bridging the Divide. As we saw in the previous chapter, while Agile brought unprecedented speed and flexibility to the development process, it left a significant void in the overall software delivery pipeline. Developers were creating software faster than ever, but the friction between development and operations teams meant that this velocity often choked at the deployment stage. The digital world was accelerating, and the traditional divide between dev and ops had become a glaring impediment to progress. It was clear that an evolution beyond Agile was necessary, a new paradigm that could ensure continuous, end-to-end flow from the initial spark of an idea to its reliable operation in the hands of the customer. The DevOps days sparked 2009, a moment of convergence. The need for a new approach didn't arise from a single corporate mandate or an academic paper. It began as a grassroots movement, born out of shared frustration and a collective desire for a better way. A pivotal moment occurred in 2009 when a Belgian IT consultant named Patrick Debois attended an Agile conference. Debois, with a background in operations, was a keen observer of the disconnect between the rapid innovations discussed by developers and the realities faced by ops teams. He noticed that while Agile principles were transforming the dev side, the ops side was still treated as an afterthought, a separate entity responsible only for keeping the lights on. Frustrated by the lack of operations representation and discussion at the conference, he decided to organize his own event. In the summer of 2009, Debois hosted the first ever DevOps Days conference in Ghent, Belgium. The name itself was a stroke of genius, a portmanteau of development and operations, instantly capturing the essence of the burgeoning movement, the necessity of integrating these two traditionally separate functions. The conference attracted a small but passionate group of individuals who shared his vision. They weren't just thinking about specific tools, but about a new culture of collaboration, automation, communication, and shared responsibility. It was a space where developers and operations professionals could finally discuss their common frustrations, share experiences, and brainstorm solutions together, for the first time on an equal footing. The energy was palpable. The attendees recognized that the problem wasn't a lack of effort from either dev or ops, but a systemic issue rooted in siloed thinking, misaligned incentives, and a lack of shared understanding. The initial discussions at DevOps Days planted the seeds for the movement, emphasizing that the solution wasn't just about better tools, but fundamentally about a better way for people to work together. The influence of the Phoenix Project, storytelling a revolution. While DevOps Days provided the conceptual framework, the wider industry truly began to grasp the depth and potential of the DevOps movement with the publication of the Phoenix Project, a novel about IT, DevOps, and helping your business win in 2013. Authored by Gene Kim, Kevin Bayer, and George Spafford, this book did something groundbreaking. It presented complex IT and organizational theories as a compelling, easy-to-read business novel. The book told the story of Bill, an IT manager thrust into the deep end when his company's struggling Phoenix Project threatens to sink the entire business. Through Bill's journey, the authors vividly illustrated the dysfunctional realities of traditional IT organizations. The constant firefighting, the blame games, the endless bottlenecks, and the devastating impact these issues had on business value. More importantly, it showed, rather than just told, how applying concepts from manufacturing, like lean principles and the theory of constraints, could revolutionize IT operations. The Phoenix Project introduced the industry to the concept of the three ways, which became the guiding principles of DevOps. The first way, flow, optimizing the entire value stream from ideas to production. The second way, feedback, creating and amplifying feedback loops within the system. The third way, continuous learning and experimentation, fostering a generative culture of high trust and continuous improvement. These three powerful concepts are so central to DevOps that we will dedicate an entire chapter to them later in this book. By weaving these principles into a relatable narrative, the Phoenix Project allowed a vast audience to grasp the organizational and cultural transformations required for DevOps success. It demonstrated that DevOps wasn't just a technical exercise. It was about fundamentally changing how people interacted, how work flowed, and how organizations learned. It highlighted that the biggest barriers to effective software delivery were often people-related and process-related, not just technology-related. Core philosophy of DevOps. Beyond tools, it's about culture. From these early days, a core philosophy solidified for DevOps, one that transcends specific tools or technologies. While automation and technical practices are crucial, the heart of DevOps lies in profound shifts in culture and mindset. Collaboration and communication. At its core, DevOps is about breaking down the silos that separated dev and ops. It's about fostering an environment where these teams, and indeed all teams involved in the software lifecycle, communicate openly, share knowledge, and work together towards common goals. No more throwing code over the wall. Instead, it's about shared accountability and active problem-solving together. This requires empathy developers understanding the operational challenges of maintaining software, and operations teams understanding the pressures of delivering new features rapidly. Shared responsibility. The mindset transitions from "that's not my job" to "we're all in this together." The ideal is a "you build it, you run it" culture, where the teams that develop the software are also deeply involved in its operation and ongoing maintenance. This instills a greater sense of ownership, ensures faster identification and resolution of issues, and ultimately leads to more robust software. Continuous improvement. DevOps champions the idea that there's always a better way. It's about never being satisfied with the status quo, constantly seeking to optimize processes, improve tools, and enhance collaboration. This isn't about grand, sweeping changes, but rather small, incremental improvements adopted continuously over time. Systems thinking. Instead of optimizing individual departments or stages, DevOps encourages looking at the entire software delivery value stream as a single, interconnected system. Understanding how changes in one part of the system impact others is crucial for identifying bottlenecks, reducing waste, and improving overall flow. The initial hype Vs. Sustainable transformation. Like any nascent movement, DevOps initially faced some misconceptions. Some believed it was merely about adopting a new set of automation tools, or that it was simply Agile applied to ops. There was a period when companies thought they could buy DevOps by purchasing specific software. However, the pioneers of the movement quickly clarified that while tools were enablers, they were not the solution in themselves. The enduring truth is that DevOps is not a destination, it's a journey. It's a continuous pursuit of operational excellence, a mindset shift, and a cultural evolution that takes time, effort, and commitment from everyone in an organization. It's about changing how people interact, how work flows, and how the entire system learns and improves. With this foundational understanding of DevOps' genesis and core philosophy, we are now ready to delve deeper into its practical application. In the next chapter, we will explore the foundational pillars that allow organizations to systematically approach this transformation. Culture, automation, lean, measurement, and sharing. The CALMS framework. These principles provide the comprehensive structure for building a truly effective DevOps organization. Chapter 4. The pillars of DevOps. Culture, automation, lean, measurement, sharing, CALMS. In our previous discussions, we established that DevOps is far more than just a set of tools or a new job title. It's a fundamental change in how organizations develop, deliver, and operate software. But how does an organization embark on such a profound transformation? How does it structure its efforts and measure its progress? The answer lies in the 5 foundational principles of DevOps, often summarized by the acronym CALMS: culture, automation, lean, measurement, and sharing. These aren't isolated concepts. Instead, they are deeply interconnected pillars that collectively support a robust and thriving DevOps environment. They provide a comprehensive framework for thinking about, implementing, and continually improving your software delivery practices. C is for culture, the human heartbeat of DevOps. If there's one pillar that stands above the rest in its importance, it's culture. Technology is merely an enabler. It's the people and their interactions that truly drive successful DevOps adoption. Without a cultural shift, even the most advanced automation tools will fall flat. Building a DevOps culture means breaking down silos, moving beyond the us-vs, them mentality between development and operations, and other functions like quality assurance and security. It's recognizing that everyone on the team shares a common goal, delivering value to the customer. This often means actively fostering empathy developers, understanding the operational challenges of maintaining systems, and operations teams appreciating the pressures of rapidly delivering new features. Trust and transparency. Fostering an environment where team members feel safe to voice concerns, admit mistakes, and take calculated risks without fear of punishment. This is often referred to as psychological safety. When people feel psychologically safe, they are more likely to innovate, learn from failures, and contribute their best work. Shared vision and goals. Aligning teams around common objectives that benefit the entire organization, rather than optimizing for individual department metrics. For example, instead of dev being measured solely on delivering features and ops on uptime, both are measured on customer satisfaction, software reliability, and speed of delivery. Blameless postmortems. When an incident occurs, an outage, a bug in production, the focus is on understanding why it happened, not who caused it. The goal is to identify systemic issues, process failures, or communication breakdowns, and then learn from them to prevent recurrence. An anecdote often cited is when a major service outage was traced back to a specific, complex configuration change made by an engineer who had skipped a step. Instead of punitive action, the team collaboratively built automated checks and improved the documentation process to ensure such a slip wouldn't happen again. The focus was on improving the system, not punishing the individual. O is for automation, the engine of efficiency. If culture is the heart, automation is the muscle. The speed and reliability central to DevOps would be impossible without ruthlessly automating repetitive tasks. Why automate? Because manual processes are slow, prone to human error, and generally boring, leading to disengagement. Automation eliminates toil, frees up valuable human time for more complex and creative problem-solving, and ensures consistency. Key areas where automation plays a pivotal role include continuous integration, CI, automating the process of building code and running initial tests every time a developer makes a change. Continuous delivery, CD, automating the pipeline that takes software from code, commit all the way to a production-ready state, including testing across various environments. Infrastructure provisioning, using code to automatically set up and configure servers, networks, and databases. We'll dive deeper into infrastructure as code later. Testing, automating unit tests, integration tests, performance tests, and even security tests. Monitoring and alerting, automatically collecting data on system health and triggering alerts when anomalous behavior is detected. It's crucial to remember that automation doesn't replace humans, it augments human capabilities. It's like giving our restaurant chef a professional, automated mixing machine for a complex dough. This allows the chef to perfect the recipe and flavors rather than spend hours on manual mixing. L is for lean, eliminating waste, maximizing value. Borrowing heavily from lean manufacturing principles, this pillar focuses on maximizing customer value by eliminating waste from the software delivery process. The core idea is to deliver small, frequent increments of value and to continuously improve the flow of work. Key aspects of lean in a DevOps context include minimizing work in progress, WIP, focusing on completing current tasks before starting new ones. Too much WIP leads to thrashing, context switching, and delays. Small batch sizes. Instead of building a massive release that takes months, break down work into smaller, independent pieces that can be delivered in days or weeks. This reduces risk, enables faster feedback, and makes problems easier to find and fix. It's like delivering small, fresh quantities of a new ingredient to a restaurant daily, rather than a massive, perishable bulk delivery monthly. Identifying and eliminating waste. Actively seeking out and removing non-value-adding activities. This could be anything from unnecessary meetings and redundant approvals to long waiting times between stages, excessive documentation nobody reads, or building features nobody uses. Fast feedback loops. The quicker you get feedback on a change, the quicker you can learn and adjust. This is central to the second way of DevOps. Lean is about making the journey from idea to customer as smooth and efficient as possible, clearing away obstacles and maximizing the flow of value. M is for measurement, knowledge is power. What gets measured gets managed. This old adage holds particularly true for DevOps. You cannot improve what you do not measure. The measurement pillar emphasizes the collection and analysis of data across the entire software delivery pipeline. This data provides the insights needed to identify bottlenecks, track progress, and make informed decisions. Key metrics in a DevOps environment often include deployment frequency, how often you release new code to production. Lead time for changes, the time it takes for a change to go from code committed to running successfully in production. Mean time to restore, MTTR, how quickly you can recover from a service incident or outage. Change failure rate, the percentage of changes that result in service degradation or outages. System performance metrics. Response times, error rates, resource utilization. Business metrics. How technical changes impact customer behavior or business outcomes, e.g., conversion rates, user engagement. The goal isn't just to collect data, but to use it to generate actionable insights. These insights should be shared transparently across teams, allowing everyone to understand system health, identify areas for improvement, and celebrate success. It's like the restaurant manager constantly checking sales figures, customer reviews, ingredient waste, and staff efficiency to optimize the restaurant's entire operation. S is for sharing, spreading knowledge and best practices. The final pillar, sharing, reinforces the collaborative nature of DevOps. It's about disseminating knowledge, lessons learned, and best practices across the organization. If information stays siloed within individual teams or departments, it hinders progress and innovation. Sharing encompasses a broad range of activities: documentation, creating and maintaining accessible, useful documentation for code, infrastructure, and processes. Internal communities of practice, groups of individuals who come together to share knowledge and discuss common interests, e.g., a containerization guild or a monitoring best practices group. Cross-training and mentorship, developers learning operational skills and operations engineers learning to code. Open communication channels, using collaboration tools, internal wikis, and regular meetings to ensure information flows freely. Feedback loops, actively sharing the findings from measurements, postmortems, and customer feedback across all relevant teams. Sharing ensures that everyone benefits from past successes and failures, accelerating the collective learning of the organization. It's the circulatory system that connects all the other pillars, ensuring vital information reaches every part of the body. The interconnectedness of calms. None of the CALMS pillars stand in isolation. They are deeply interdependent and reinforce each other in a continuous cycle. A culture of trust and transparency allows teams to safely implement automation. Automation provides the data necessary for measurement. Measurement identifies areas for improvement, which can then be optimized using lean principles. Insights gained through measurement and lean efforts are then shared, fostering continuous learning and reinforcing a positive culture. This symbiotic relationship forms the continuous improvement loop that defines a high-performing DevOps organization. Understanding the CALMS framework provides a powerful lens through which to view and implement the practical aspects of DevOps. In the next chapter, we will delve deeper into the philosophical underpinnings of this continuous cycle, exploring the 3 ways of DevOps, which provide further guidance on flow, feedback, and continuous learning. Chapter 5. The 3 ways: flow, feedback, and continuous learning. In the previous chapter, we explored the CALMS framework culture, automation, lean, measurement, and sharing as the foundational pillars of DevOps. These pillars provide a comprehensive guide to the various facets of a DevOps transformation. Now, we'll delve into the deeper, more philosophical underpinnings of DevOps, the guiding principles that provide a powerful mental model for understanding and implementing the CALMS components. These are articulated as the 3 ways: the first way, flow; the second way, feedback; and the third way, continuous learning and experimentation. Popularized by the Phoenix Project and further elaborated in the DevOps Handbook, these 3 ways describe the patterns of behavior and practice that lead to superior organizational performance in software delivery. They are a set of meta-principles that explain why many DevOps practices work, transcending specific tools or techniques. The first way, flow, accelerating value delivery. The first way focuses on maximizing the flow of work from the moment an idea is conceived and codified, through development and deployment, all the way to its operation in the customer's hands. Its primary goal is to accelerate the delivery of value by making the entire process faster, smoother, and more predictable. This is achieved by thinking of the software delivery pipeline as a production line, much like in lean manufacturing, and continuously optimizing it. To enable flow, organizations focus on small batch sizes. Instead of hoarding changes and releasing massive bundles of features infrequently, work is broken down into small, independent increments. This significantly reduces risk, as smaller changes are easier to test, identify issues in, and roll back if necessary. Imagine a highway where only a few cars drive at a time versus a massive traffic jam. Fewer cars mean faster travel and less likelihood of a major pileup. Limiting work in progress, WIP. When teams try to do too many things at once, they switch contexts frequently, leading to inefficiency and delays. Limiting WIP means focusing efforts on completing fewer tasks faster, rather than starting many tasks but finishing none. Continuous integration, CI. As we touched on in Chapter 4, CI is a critical enabler of flow. By integrating code frequently and automatically testing it, development teams prevent integration hell and ensure that the codebase is always in a working, releasable state. This keeps the production line of code moving smoothly. Continuous delivery, CD. This extends CI, ensuring that the software is always ready to be released to production. It involves automating the entire pipeline from code commit to deployment, effectively eliminating manual handoffs and bottlenecks. Infrastructure as code (ISC). Treating infrastructure, servers, networks, databases, as code means it can be provisioned, configured, and managed automatically, just like application code. This eliminates manual setup and configuration errors, ensuring consistency and speed in environment provisioning, which is vital for smooth flow. Minimizing handoffs. Every time work moves from one team to another, e.g., from dev to QA to ops, there's a potential for delay, misunderstanding, and error. The first way seeks to reduce these handoffs through shared tooling, shared goals, and cross-functional teams that collectively own the entire value stream. The outcome of applying the first way is a significant reduction in lead time for changes, increased deployment frequency, and a more predictable, efficient delivery process. Software moves swiftly and reliably from concept to customer. The second way, feedback amplifying learning. The second way emphasizes the creation and amplification of feedback loops throughout the entire software delivery lifecycle. Its purpose is to ensure that problems are detected as early as possible, that information flows rapidly to the right people, and that effective learning quickly takes place. This makes the system more resilient and adaptable. To enable feedback, organizations focus on monitoring and observability. Chapter 8 Deeper Dive. This involves constantly collecting data on system health, performance, and user experience. Beyond knowing if something is broken, monitoring. Observability aims to understand why it's broken, even for unforeseen issues, by analyzing metrics, logs, and traces. Automated alerts provide immediate notification of anomalies. Automated testing. Chapter 6 Deeper Dive. Beyond just unit tests, this includes a robust suite of integration, performance, acceptance, and security tests that run continuously. This provides rapid feedback on the quality and functionality of every change. Customer feedback channels. Actively seeking and integrating feedback from end users, whether through direct communication, A/B testing, or feature usage analytics. This ensures that the software being built truly meets user needs. Blameless postmortems. When an incident occurs, the focus is not on finding blame, but on understanding the systemic causes that led to the problem. The goal is to learn from the failure, share those learnings transparently, and implement changes that prevent recurrence. This creates a culture where people feel safe to report errors, knowing it will lead to improvement, not punishment. Shift left principle, Chapter 9 Deeper Dive. This means integrating quality and security checks earlier in the development process, rather than leaving them until the end. The sooner a defect or vulnerability is found, the cheaper and easier it is to fix. By amplifying feedback, organizations can identify problems quickly, respond effectively, learn from mistakes, and continuously improve the quality and reliability of their systems. This ensures that the organization can react swiftly to unforeseen events and continuously refine its understanding of its systems and customers. The third way, continuous learning and experimentation, fostering a generative culture. The third way builds upon the first two, fostering a culture of continuous learning, experimentation, and high trust. It's about creating an environment where people feel safe to take risks, learn from both successes and failures, and constantly seek new ways to improve. This creates a resilient, innovative, and adaptive organization. To enable continuous learning and experimentation, organizations focus on generative, high-trust culture. This is the cultural element of CALMS brought to life. It's an environment where information flows freely, people collaborate effectively, and problems are genuinely shared and solved without fear of retribution. Leaders model curiosity and vulnerability. Experimentation. Encouraging teams to hypothesize, test ideas, measure results, and learn rapidly. This could involve A/B testing new features, trying out new tools or processes, or conducting small, controlled experiments to validate assumptions. The emphasis is on building a scientific approach to organizational improvement. Practice and repetition. Just like a musician practices scales to master an instrument, teams continuously refine their skills and processes through repeated execution and reflection. This builds muscle memory for efficient and reliable operations. Learning from catastrophes. turning incidents and outages into profound learning opportunities for the entire organization. This goes beyond just fixing the immediate problem, striving to understand the deeper systemic flaws that contributed to it. Sharing knowledge across boundaries, active dissemination of lessons learned, best practices, and new insights across teams and departments. This prevents knowledge silos and accelerates collective organizational intelligence. The ultimate outcome of the third way is an organizational capability for continuous improvement and innovation. It fosters a workforce that is not only skilled, but also deeply engaged, psychologically safe, and constantly striving for excellence. The virtuous cycle of the three ways. The three ways are not sequential steps. They are interdependent principles that form a continuous, reinforcing cycle. Flow enables faster feedback. When work moves quickly, you get results and insights rapidly. Faster feedback allows for more effective continuous learning and experimentation. Knowing what worked, or didn't, quickly is essential for learning. Continuous learning and experimentation lead to improvements in flow. As the organization learns, it optimizes its processes, tools, and culture, making the flow of value even smoother and faster. This virtuous cycle is the engine of the DevOps revolution. It explains why organizations that truly embrace DevOps principles achieve not just technical excellence, but profound business agility, resilience, and employee satisfaction. With this understanding of the fundamental principles, we are now ready to explore the specific technical practices that bring these principles to life, starting with the very core of rapid software delivery: continuous integration and continuous delivery. Chapter 6: Continuous integration and continuous delivery, the engine of speed. Let's be honest. In the traditional software world, release day was often a term uttered with a mix of dread and exhaustion. It conjured images of late-night cutovers, manual checklists, frantic phone calls, and the lingering fear that something, somewhere, was about to break. This chapter introduces two of the most tangible and transformative practices in the DevOps toolkit: continuous integration, CI, and continuous delivery, CD. They are the very embodiment of the first way, optimizing flow, and the engine that powers the speed, reliability, and frequency of software releases. The pain point: integration hell and infrequent releases. Before we dive into the magic of continuous integration and continuous delivery, let's take a moment to appreciate the pain they alleviate. Imagine a grand construction project, perhaps a towering office building. In the traditional way of building software, many different teams would be assigned separate sections of the building. One team for the foundation, another for the first floor, a third for plumbing, and so on. Each team works independently for months. The foundation team builds their part, then the first floor team builds theirs, and so on. Crucially, they don't really see how their work integrates with everyone else's until the very end. The plumbing team, working on the 10th floor, might design their pipes assuming the walls are a certain thickness, only to find out months later that the wall team built them differently lower down, creating a huge, unexpected problem. This is a bit like integration hell in software. Historically, individual developers or small teams would work on a specific feature or piece of code for weeks or even months in isolation. They might be working on different parts of the same large application, one designing the user login, another building the payment system, a third creating the search functionality. Each developer, confident in their own work, would then try to combine their code with everyone else's. What inevitably followed was a chaotic and frustrating period known as integration hell. Suddenly, the elegant code written by one developer might clash directly with another's. Different versions of libraries, conflicting definitions of data, or simply unexpected interactions between pieces of logic would lead to a cascade of errors. Imagine trying to fit puzzle pieces together, only to discover that they were all cut by different machines, expecting different sizes and shapes. Finding these integration problems late in the cycle was not just frustrating, it was incredibly expensive. The longer a bug or conflict persists, the more entwined it becomes with other parts of the system, making it exponentially harder and more costly to untangle. It's like trying to fix the plumbing in a completed skyscraper. You might have to tear down walls that were just finished. This protracted, painful process became the very problem continuous integration and continuous delivery were designed to solve. They represent a fundamental shift from infrequent, large, and risky code merges to small, frequent, and low-risk integrations. Continuous integration, CI, the daily habit of collaboration. Continuous integration, or CI, is the first step in breaking free from integration hell. At its heart, CI is a simple yet powerful practice. Developers integrate their code into a shared repository, frequently, ideally multiple times a day. And with each integration, an automated process kicks in to verify that the new code plays nicely with existing code. Think of it like this. Instead of each construction team working in isolation for months, they now constantly check their work against a central blueprint. As soon as the foundation team pours a section, the first floor team checks their design against it. If there's an incompatibility, they find it right away, when it's just a small patch of concrete, not a fully constructed floor several months down the line. Here's how CI works in practice. The shared repository version control system. At the core of CI is a centralized system, often called a version control system, like Git, conceptually, where all the application's code lives. This repository is the single source of truth for the entire project. Developers check out the latest version of the code, make their changes, and then check in or commit their changes back to this shared repository. Automated build. Every time a developer commits new code, the CI system automatically takes that code and all the existing code and performs a build. For compiled languages, this means turning the human-readable code into a machine-executable program. For other types of software, it might involve preparing packaged files or bundles. The key is that this process is entirely automated and consistent. If the build fails, meaning the code can't even be compiled or packaged, the developer is notified immediately. This is the first, most basic check. Automated testing. Immediately after a successful build, the CI system runs a suite of automated tests. These are typically unit tests, small tests that verify individual pieces of code work as expected, and integration tests, tests that check if different parts of the code work together. This step is crucial. It's not enough for the code to compile, it must also work as intended. If any of these tests fail, the developer who committed the problematic code is alerted instantly. Fast feedback. The cornerstone of CI is speed. The entire process, from code commit to build and test results, should happen within minutes, ideally. This rapid feedback loop is invaluable. When a developer gets immediate notification that their recent code change broke something, the problem is fresh in their mind, and the amount of new code to debug is small. This makes fixing the issue dramatically easier and faster than discovering it days or weeks later. The benefits of continuous integration are profound. Early detection of issues. Integration conflicts and bugs are caught almost immediately, preventing them from growing into debilitating problems. Reduced risk. Instead of large, risky merges, you have frequent, small, low-risk integrations. Consistent builds. Everyone is always working with and building against the same, most up-to-date codebase. Increased confidence. Teams gain confidence in the stability of their codebase because it's constantly being validated. Better collaboration. CI naturally fosters collaboration because developers are constantly sharing and verifying each other's work. Ultimately, continuous integration shifts the burden from a painful, manual integration day to a continuous, automated background process that supports teamwork and quality. It's the essential heartbeat of rapid software development. Continuous delivery, CD, always ready to release. Continuous delivery, CD, takes the success of continuous integration a significant step further. While CI ensures that your code is always integrated and tested, CD ensures that your software is always in a releasable state. It automates the entire process of getting a software change from your version control system all the way to a state where it is ready to be deployed to a production environment. Think back to our construction project. CI ensures that individual sections of the building, foundations, walls, plumbing, are built correctly and integrate well. CD takes it to the next level. It ensures that at any given moment, the entire building can be handed over to the client. All systems are checked, all inspections passed, and the keys are ready to be turned over. The CD process is often visualized as an automated delivery pipeline, or simply a pipeline, through which every code change flows. Build stage from CI. The pipeline begins when a new code change is committed and passes the continuous integration checks, meaning it builds successfully and passes all unit and integration tests. This produces a verified artifact, which is the deployable package of your software. Expanded automated testing. Beyond the quick tests in CI, the CD pipeline runs a more comprehensive suite of automated tests. This can include performance tests, checking how the application behaves under various loads; security tests, scanning for vulnerabilities; acceptance tests, verifying that the new features work as expected from a user's perspective. These tests run against environments that increasingly resemble the final production environment. Deployment to staging testing environments. The pipeline automatically provisions or deploys the application to pre-production environments, often called staging, QA, or UAT environments. These environments are designed to mimic the production setup as closely as possible in terms of hardware, software, and configuration. Automated verification. Once deployed to these staging environments, more automated checks and tests are performed. This verifies not only the application itself, but also its interaction with other systems and external services in a realistic setting. Ready for production. If the software passes all these automated gates, it is now considered production-ready. It sits waiting, fully validated, for a simple manual decision to release it to live users. This manual step might be a click of a button by a product owner or a business decision to deploy. Continuous deployment, CD, the ultimate automation, optional. Continuous deployment is a further extension of continuous delivery. In continuous deployment, every change that successfully passes all stages of the automated pipeline is automatically released to production, without human intervention. This means if a developer commits code, and it passes all the automated build, test, and verification steps, it will automatically go live to users. This is the fastest feedback loop possible and represents the pinnacle of automation. It's not for everyone, requiring extremely high confidence in automated testing and robust monitoring. Companies like Flickr and Amazon pioneered this, often deploying changes dozens or even hundreds of times a day. The impact on teams and business. The adoption of continuous integration and continuous delivery marks a profound shift in how software organizations operate. No more dreaded release weekends. The pain and risk associated with large, infrequent releases are dramatically reduced. Deployments become mundane, low-risk events that can happen at any time. Faster time to market. New features and bug fixes can be delivered to customers much more quickly, allowing businesses to respond rapidly to market demands and gain a competitive edge. Improved software quality. Constant, automated testing and small changes mean that bugs are caught early and often, leading to more reliable and stable software. Increased team confidence and morale. Developers and operations teams gain confidence in their ability to deliver working software consistently. This reduces stress and shifts focus from firefighting to innovation. CI/CD are not just technical practices. They embody the automation and lean principles of CALMs, enabling efficient flow and providing rapid feedback, foundational to the three ways. They are the backbone of any modern, high-performing software organization, transforming the act of releasing software from a nail-biting marathon into a continuous, confident stride. Chapter 7, Infrastructure as Code and Cloud Native, Building Resilient Systems. In the world of software, the application code that developers write is only one piece of the puzzle. That code needs a home, a place to run, store data, and connect with users. This home is known as infrastructure. Servers, networks, databases, storage, and all the underlying components that make software accessible and functional. Historically, managing this infrastructure was a laborious, manual process, often divorced from the development of the software itself. This chapter explores two powerful concepts that have revolutionized infrastructure management, making it an agile, automated, and scalable extension of the DevOps philosophy. Infrastructure as Code (ISC) and the cloud-native paradigm. Together, they transform how organizations build, deploy, and operate resilient systems. Infrastructure as code, ISC. Defining your world with text. Imagine you're running our restaurant from the earlier analogy, and you need to set up a new kitchen. The traditional approach would involve a team of specialists manually installing each oven, wiring each appliance, setting up the ventilation system, and configuring every tap and drain. It would be a meticulous, time-consuming process, prone to human error, and difficult to precisely replicate for a second identical kitchen. That's precisely how IT infrastructure was managed for decades. An operations engineer would manually log into servers, install operating systems, configure network settings, set up databases, and install application dependencies. This manual approach created several significant problems: inconsistency, configuration drift. Different environments, development, testing, production, would inevitably diverge over time. A critical bug might appear in production that couldn't be replicated in testing because the environments were subtly different. This was akin to having slightly different kitchen setups in each branch of your restaurant, leading to unpredictable dish quality. Human error. Manual tasks are inherently prone to mistakes, leading to misconfigurations, security vulnerabilities, or performance issues. Slowness. Setting up a new environment could take days, weeks, or even months, severely hindering the speed of development and testing. Lack of auditability. There was often no clear, versioned record of exactly how an environment was configured, making troubleshooting difficult and compliance burdensome. Infrastructure as code, ISC, is the revolutionary answer to these problems. It treats your infrastructure, servers, networks, databases, load balancers, firewalls, everything as if it were application code. This means defining and provisioning it using machine-readable definition files, rather than through manual processes or interactive configuration tools. Here's what that means in practice. Version control. Just like application code, your infrastructure definitions are stored in a version control system, like Git. This creates a complete, auditable history of every change made to your infrastructure, including who made it, when, and why. Automation. Once defined in code, your infrastructure can be automatically provisioned, updated, or torn down. This eliminates manual tasks and vastly increases speed and consistency. Reproducibility. With ISC, you can spin up identical environments repeatedly and on demand. This ensures that your development, testing, and production environments are consistent, drastically reducing "it works on my machine" issues. It's like having a precise architectural blueprint for your kitchen that allows you to clone it perfectly every single time. Idempotence. An ISC script is designed to achieve a desired state. Running the same script multiple times will always lead to the same result, without unintended side effects. This ensures configurations are stable even if a deployment is interrupted or run multiple times. The benefits of ISC are vast: speed and efficiency. Rapidly provision new environments for development, testing, or production. Consistency and reliability. Eliminate configuration drift and human errors, ensuring all environments behave predictably. Reduced risk. Infrastructure changes are reviewed and tested like code, reducing the likelihood of production outages. Cost savings. Optimize resource usage by spinning up environments only when needed and tearing them down when not. Documentation and auditability. The code itself serves as living documentation of your infrastructure, providing a clear audit trail. The cloud-native paradigm, built for agility and scale. While ISC provides the blueprint for automated infrastructure, the emergence of cloud computing provided the flexible, on-demand canvas upon which to paint these infrastructure definitions. Cloud computing isn't just about moving your servers from your basement to a data center owned by someone else. It's a fundamental shift in how computing resources are accessed, provisioned, and managed. The term cloud native describes applications and infrastructure designed specifically to leverage the capabilities of cloud computing. This paradigm is built around principles of agility, scalability, and resilience, key characteristics that make cloud-native environments ideal for DevOps. On-demand resources. Cloud providers offer computing power, storage, and networking as utilities. You can provision resources almost instantly and scale them up or down with demand, paying only for what you use. This elasticity is crucial for handling fluctuating user loads and rapidly scaling businesses. Resilience and fault tolerance. Cloud providers build their infrastructure with redundancy and self-healing mechanisms. Cloud-native applications are designed to be fault-tolerant, meaning they can continue to function even if individual components fail. Managed services. Cloud platforms offer a vast array of managed services for databases, messaging queues, artificial intelligence, and more. This offloads the operational burden of managing complex software, freeing up teams to focus on core business logic. Microservices architectures. The cloud-native movement often goes hand in hand with microservices, where large, monolithic applications are broken down into smaller, independent, and loosely coupled services. Each microservice can be developed, deployed, and scaled independently, offering unprecedented agility. The cloud-native paradigm is also deeply intertwined with powerful new technologies, explained conceptually for clarity. Containers. Imagine a sealed, standardized shipping container for software. A container packages an application along with all its dependencies into a single, portable unit. This ensures that the application behaves exactly the same regardless of where it's deployed, from a developer's laptop to a massive cloud server. This consistency is a DevOps dream. Container orchestration. For applications built with many containers, you need a system to manage them. Container orchestrators, like Kubernetes, conceptually automate the deployment, scaling, healing, and networking of containerized applications. They act as the port authority, managing thousands of shipping containers, ensuring they get to their destinations and interact efficiently. The symbiotic relationship. ISC and cloud-native drive DevOps. The true power emerges when infrastructure as code and the cloud-native paradigm are used together. The cloud provides the vast, flexible, and on-demand pool of resources. You no longer need to buy physical servers, install them, and manage their cooling and power. ISC provides the automated, repeatable, and version-controlled blueprint for precisely defining how you want to use those cloud resources. It's how you tell the cloud exactly what kind of servers, networks, and databases you need, and how they should be configured. Together, they form a formidable combination that directly addresses the goals of DevOps. Rapid environment provisioning. Developers can spin up personal development environments or dedicated testing environments in minutes directly from version-controlled ISC templates. This accelerates the entire development and testing lifecycle. Consistent deployments. Because infrastructure is defined in code, every deployment, application, and its underlying infrastructure is consistent, reducing works on my machine problems and ensuring that what was tested is exactly what runs in production. Resilience and scalability. Leveraging cloud-native features and ISC, you can design systems that automatically scale up or down with demand and recover gracefully from failures, leading to much more reliable services. Operations as engineering. The role of operations shifts from manual IT administration to sophisticated automation engineers. They are no longer constantly firefighting, but rather designing and improving the automated systems that manage the infrastructure. This powerful duo allows organizations to not only deliver software faster, but to build and operate robust, self-healing, and scalable systems that can adapt rapidly to change. It's a testament to how treating the entire stack, from application to underlying hardware, as code, fundamentally changes the capabilities and resilience of modern software delivery. Chapter 8. Monitoring, Metrics, and Observability. Seeing your systems clearly. In DevOps, speed and automation are paramount, but they come with a critical prerequisite: visibility. Once software is flowing rapidly through automated pipelines and being deployed to dynamic, cloud-native infrastructures, how do you know if it's actually working well? How do you ensure it's providing value to customers? And critically, how do you know before your customers do if something goes wrong? This is where monitoring, metrics, and observability come into play. They are the feedback loop of the second way of DevOps, providing the essential insights needed to understand system health, identify issues, and drive continuous improvement. The basics of monitoring: keeping a watchful eye. In the traditional IT world, monitoring was often reactive. You'd set up alerts for when a server crashed or a hard drive filled up, then wait for an email or pager to notify you. The goal was simply, is it up? This approach often meant that users would experience a problem long before the operations team became aware of it, leading to frustrating phone calls and scramble mode troubleshooting. Monitoring in a DevOps context is far more proactive and comprehensive. While it still tracks the health of systems and applications, it aims to do so continuously, providing real-time data that helps teams anticipate problems and respond quickly. What gets monitored? A wide array of information, including system resources. Is the server's CPU overworked? Is it running out of memory or disk space? How much network traffic is it handling? Application performance. How fast are user requests being processed? What is the error rate for a specific function? How many users are active on the site? Business metrics. Beyond technical health, true DevOps organizations also monitor metrics tied directly to business value. How many items are being added to a shopping cart per minute? What's the conversion rate on a specific landing page? How many new users registered today? The outputs of monitoring often feed into alerting systems. These systems are configured to notify the right people, e.g., the team responsible for that specific service. When predefined thresholds are crossed, e.g., CPU usage consistently above 80% for 5 minutes. The trick to effective alerting is to avoid alert fatigue. Only alert on truly actionable items that require human intervention, not every minor fluctuation. Many non-critical events should be handled automatically or simply logged for later analysis. Finally, dashboards are essential for visualizing this collected information. A well-designed dashboard provides key stakeholders, from developers to business leaders, with a clear, holistic view of system health and performance at a glance. Metrics. The data points that tell a story. Metrics are quantifiable measurements captured over time. They are the raw data that allows teams to understand trends, diagnose problems, and validate the impact of changes. In a DevOps world, metrics are crucial for data-driven decision-making. Why do metrics matter so much? Early warning system. Consistent tracking of metrics allows teams to spot subtle changes or anomalies that could indicate an impending problem, long before it becomes a full-blown outage. Performance analysis. Metrics provide the data needed to understand how systems are performing and to identify bottlenecks or inefficiencies that can be optimized. Validating changes. After a new feature is deployed or a system is optimized, metrics can objectively prove whether the change had the desired positive effect or an unintended negative one. Informing business decisions. By linking technical metrics to business outcomes, organizations can make better decisions about where to invest resources and what features to prioritize. In the DevOps community, a specific set of metrics, often referred to as the DORA metrics, after the DevOps research and assessment team, have become critical indicators of an organization's software delivery performance. Deployment frequency, how often an organization successfully delivers code to production. High frequency indicates agile, low-risk releases. Lead time for changes. The time it takes for new code to go from committed to running in production. Shorter lead times mean faster iteration and response. Mean time to recover, MTTR. The average time it takes to restore service after a disruption or outage. A low MTTR indicates efficient incident response and recovery. Change failure rate. The percentage of changes to production that result in degraded service or require remediation. A low failure rate signifies high quality and stable deployments. These metrics, which reflect an organization's ability to achieve flow, feedback, and continuous learning, are far more telling than traditional measures like lines of code written or uptime percentage in isolation. Beyond these high-level indicators, technical metrics typically fall into categories like rate, how often an event occurs, e.g., requests per second, transactions per minute. Error, the count or percentage of errors, e.g., failed requests, error codes. Duration, how long an operation takes, e.g., response time, processing time. Logs, the detailed narrative. While metrics provide aggregate trends and summaries, Logs offer the detailed narrative of what happened within a system. Logs are time-stamped records of events that occur within applications and infrastructure components. Everything from a user logging in, to a database query running, to a system error being triggered. The purpose of logs is to provide granular context for debugging, troubleshooting, and understanding specific system behaviors. When a metric alerts you to a problem, e.g., an increase in error rate, logs are often the first place you go to find the specific error messages, user IDs, or other contextual information needed to diagnose the root cause. The challenge with logs is their sheer volume and often inconsistent formats, especially in distributed systems. For this reason, centralized logging solutions are critical. These systems aggregate logs from all sources, servers, applications, databases, into a single, searchable repository, making it far easier to analyze vast amounts of data and pinpoint specific events quickly. Observability. Understanding the unforeseen. While monitoring tells you if something is wrong with your system, observability helps you understand why it's wrong, even for problems you haven't explicitly anticipated. It's a deeper, more profound level of understanding. Think of it this way: your car has a check engine light monitoring. It tells you if there's a problem. Observability, on the other hand, is like being able to connect to your car's internal computer system and pull up detailed telemetry, performance data, sensor readings, error codes, internal process traces. Even if it's a brand new, never-before-seen engine issue, the collected data allows a skilled mechanic to diagnose why the light is on and how to fix it. Observability encompasses three core pillars, sometimes referred to as the 3 pillars of observability. Metrics, as discussed previously, providing the summarized high-level trends. Logs, as discussed previously, providing the detailed event narratives. Traces, following a single transaction or user request as it travels through multiple services, microservices, databases, and network hops. This provides an end-to-end view of a request's journey, making it invaluable for diagnosing issues in complex, distributed systems. Designing an observable system means collecting the right kind of data so that, even when an unknown problem arises, you have enough information to explore and understand its internal state from its external outputs. It allows teams to debug and troubleshoot complex systems without needing to manually inspect their internal workings. Implementing effective feedback loops. For monitoring, metrics, and observability to truly support a DevOps culture, they must be operationalized. Automate data collection. Integrations with monitoring tools are built into the CI/CD pipeline and infrastructure provisioning process. Visualize data. Clear, actionable dashboards are provided to relevant teams, allowing them to self-service information. Operationalizing insights. Data is not just collected, it's acted upon. Metrics identify areas for improvement, logs and traces aid in root cause analysis, and these insights feed directly into continuous improvement initiatives. Blameless postmortems. Using metrics and logs to thoroughly understand incident root causes in a no-blame environment, fostering learning and resilience. The business value of visibility. The investment in robust monitoring, metrics, and observability pays immense dividends beyond just technical stability. Proactive problem solving. Identifying and fixing issues before they impact customers saves reputation and revenue. Data-driven decisions. Informed decisions about features, resource allocation, and operational improvements. Enhanced customer satisfaction. Reliable, high-performing software leads to happier users. Increased innovation. Teams can experiment more confidently knowing they have full visibility into the impact of their changes. Shared understanding. Consistent data fosters empathy and collaboration across development, operations, and business teams, as everyone is looking at the same objective truth about system health. In essence, monitoring, metrics, and observability provide the eyes and ears for your DevOps journey. They ensure that while you're moving fast, you're also moving in the right direction, with clear understanding and the ability to adapt to any challenge. Chapter 9, Security in a DevOps World. Shifting left, DevSecOps. In the past, security was often viewed as the final checkpoint before software deployment, a necessary evil, or even a bottleneck. Teams would develop software, pass it to quality assurance, and then, almost as an afterthought, hand it over to a dedicated security team for review. This typically involved lengthy audits, penetration testing, and vulnerability scanning, often revealing critical flaws just days or hours before a planned release. The result was either frustrating delays, costly last-minute fixes, or worse, vulnerabilities making it into production. The traditional approach to security simply doesn't scale in a world of continuous delivery and rapid iteration. When development teams are deploying changes multiple times a day or even dozens of times a week, a security model that relies on periodic manual gate checks becomes an insurmountable bottleneck. This challenge led to the emergence of DevSecOps, a paradigm where security is not an afterthought, but an integral, continuous part of the entire software development lifecycle. The challenge with traditional security approaches. Let's briefly revisit why traditional security models often clashed with the agile, fast-paced nature of modern software delivery. Late-stage discovery. Finding security vulnerabilities just before launch is incredibly expensive to fix. It's like finding a critical structural flaw in a building after the roof is on and all the interior walls are painted. The later a defect is found, the more exponential it costs to remediate. Security as a separate entity. When security is handled by a siloed external team, developers often lack direct security awareness and education. They might see security as a hurdle to overcome rather than a shared responsibility. This creates another wall of confusion, similar to the DevOps divide. Reactive posture. Traditional security often focuses on responding to breaches or threats after they occur, rather than proactively preventing them throughout the development process. Lack of context. Security teams, detached from the day-to-day development, might not fully understand the operational context or the business requirements influencing design decisions, leading to impractical security recommendations. What is DevSecOps? Shifting security left. DevSecOps isn't a separate team or a new set of tools to buy. It's an extension of the core DevOps principles of collaboration, automation, and continuous improvement, applied specifically to security. The central tenet of DevSecOps is shifting left. Shifting left means integrating security activities, education, and considerations as early as possible in the software development lifecycle, far to the left of the traditional security gates diagram. Instead of waiting until deployment to perform security checks, DevSecOps embeds security from the very beginning, during planning and design, through coding, testing, and deployment, and finally into ongoing operations. Imagine building a car. In the traditional approach, you'd build the entire car, then crash test it and add safety features. Shifting left means designing safety into every single component from the initial drawing board, using stronger metals, designing crumple zones, integrating intelligent braking systems long before the car is assembled. Key principles and practices of DevSecOps. DevSecOps operationalizes security throughout the development and operations process. Here are some key principles and practices. Culture of shared responsibility. Just as DevOps encourages Dev and Ops to share responsibility for software delivery, DevSecOps expands this to include security. Everyone in the development pipeline becomes responsible for security, not just a dedicated security team. This is fostered by security champions, developers or operations staff who are enthusiastic about security and act as go-to resources and advocates within their teams. Security education and awareness. Providing continuous training for developers on secure coding practices, common vulnerabilities, and threat modeling. Cross-functional collaboration. Security teams work with development and operations teams, guiding them, providing tools, and embedding security requirements, rather than imposing them from afar. Automated security testing. Manual security reviews simply cannot keep up with the pace of modern development. DevSecOps heavily relies on automating security testing and embedding it directly into the CI/CD pipelines. Static application security testing, SAST. Scans source code, bytecode, or binary code to identify security vulnerabilities without actually executing the program. This provides rapid feedback to developers on potential flaws in their code. Dynamic Application Security Testing, DAST, tests a running application from the outside, looking for vulnerabilities that an attacker might exploit. It simulates attacks to find weak points. Software Composition Analysis, SCA, automatically identifies open-source components used in an application and checks them against known vulnerability databases. Given that modern applications rely heavily on open-source libraries, this is crucial. Container Security Scanning automatically scans container images, which we discussed in Chapter 7, for known vulnerabilities or misconfigurations before they are deployed. Infrastructure as Code Security, analyzing ISC templates to ensure that the infrastructure being provisioned adheres to security best practices and doesn't introduce vulnerabilities. Secure by design. Security isn't patched on at the end. It's considered from the very inception of an idea or feature. Threat modeling. During the design phase, teams actively identify potential threats and vulnerabilities to the system and design mitigations proactively. Security requirements. Security non-functional requirements, e.g., data encryption, authentication mechanisms, are integrated directly into development backlogs and user stories. Continuous monitoring and response. Post-deployment security is also integrated. Security information and event management, SIEM, aggregating and analyzing security logs and events from across the infrastructure to detect suspicious activity. Automated incident response, implementing automated playbooks to respond to identified security threats, such as isolating compromised systems or triggering alerts. Least privilege and immutable infrastructure. Core security principles are reinforced by DevOps. Least privilege, ensuring that users, applications, and systems only have the minimum necessary access rights required to perform their functions. Immutable infrastructure, replacing entire servers or components with new, correctly configured ones rather than updating existing ones. This minimizes configuration drift and ensures a consistent, secure baseline. The benefits of DevSecOps. The integration of security into DevOps brings significant advantages. Faster time to release secure code. By detecting and fixing security issues early, the development process remains fluid, avoiding costly delays at the end. Reduced risk and improved compliance. Proactive and continuous security means fewer vulnerabilities make it to production, leading to a stronger security posture and easier compliance with regulations. Cost savings. Preventing security breaches is far more cost-effective than responding to them after they occur. Early detection of vulnerabilities drastically reduces remediation costs. Enhanced trust. Customers and stakeholders gain greater confidence in the security of the software and the organization. Fosters a security-aware culture. Security becomes part of everyone's job, leading to a more security-conscious workforce and embedding secure behaviors. Overcoming the challenges. Implementing DevSecOps is not without its hurdles. It requires investment in training to address skill gaps, particularly for developers who may not have extensive security backgrounds. Integrating security tools seamlessly into existing CI/CD pipelines can be complex, and striking the right balance between robust security checks and maintaining development speed is an ongoing challenge. However, by starting small, automating where possible, fostering a collaborative culture, and continuously learning, organizations can effectively shift security left. In a world where cyber threats are constantly evolving, DevSecOps is no longer a luxury, but a necessity for any organization serious about delivering value continuously and securely to its customers. Chapter 10. Building a DevOps culture, people, processes, and psychology. We've discussed the technical pillars of DevOps automation, continuous integration and delivery, infrastructure as code, robust monitoring, and shifting security left. These are powerful tools and practices that enable a new way of building and running software. However, time and again, organizations attempting a DevOps transformation discover that the most significant hurdles are not technical, but cultural. As we noted in Chapter 4, culture is the very first pillar of CALMS, and for good reason. Culture eats strategy and tools for breakfast. This chapter dives deep into the human element of DevOps, exploring how to build a collaborative, psychologically safe, and continuously improving culture. Breaking down the silos, fostering collaboration and empathy. The fundamental problem that DevOps sets out to solve is the wall of confusion between development and operations. This wall wasn't just physical. It was deeply ingrained in organizational structures, incentives, and even the language used. Developers, driven by features and speed, often clashed with operations, who prioritized stability and risk reduction. This led to an us versus them mentality, characterized by blame games, mistrust, and a lack of empathy for each other's challenges. Overcoming this deeply entrenched resistance to change is paramount. People naturally gravitate towards what's familiar and predictable. Changing long-standing work habits, team structures, and ways of thinking can be unsettling. To bridge this historical gap, organizations need to employ strategies that foster collaboration and empathy. Shared goals and metrics. Instead of dev and ops having separate, sometimes conflicting, goals, align them around common business objectives. Both teams should be measured on things like customer satisfaction, swift recovery from incidents, and the overall value delivered to the business, rather than just individual department metrics. Cross-functional teams. Where possible, restructure teams to include members from both development and operations disciplines, and often QA and security too. These small, empowered teams own a product or service end-to-end, from development through operation. This forces daily collaboration and a natural understanding of each other's worlds. Imagine a single pit crew for a race car, where every mechanic understands not just their specialty, but also how their work impacts the rest of the car's performance. Physical or virtual proximity. Encourage developers and operations engineers to sit together, if possible, or use shared virtual communication channels and collaboration tools. This facilitates informal communication, quick questions, and a sense of shared purpose. Job rotation shadowing. Have developers occasionally spend time on call with operations teams and vice versa. There's nothing like experiencing the pressure of an outage or the complexities of a new feature rollout to build empathy and mutual respect. Psychological safety, the foundation of high-performing teams. At the heart of a truly collaborative and continuously improving culture is psychological safety. Pioneered by Harvard Business School professor Amy Edmondson, psychological safety is defined as a shared belief held by members of a team that the team is safe for interpersonal risk-taking. In simple terms, it's the belief that you won't be punished or humiliated for speaking up with ideas, questions, concerns, or mistakes. Why is psychological safety so critical for DevOps? Enables experimentation. DevOps thrives on rapid experimentation and learning. If team members fear failure or ridicule, they will be hesitant to try new approaches, propose innovative solutions, or admit when something didn't work. Fosters honest feedback. Without psychological safety, feedback loops break down. People will withhold critical information about bugs, operational issues, or process inefficiencies if they fear being blamed. Improves problem solving. Teams with high psychological safety can openly discuss problems, brainstorm solutions, and challenge assumptions without resorting to blame or defensiveness. Allows learning from mistakes. Crucially, psychological safety is the bedrock of blameless postmortems. When an incident occurs, the team can focus on understanding the systemic and process failures that contributed to it, rather than scapegoating individuals. This leads to genuine learning and prevents recurrence. How do leaders cultivate psychological safety? Leaders play a pivotal role. They must model vulnerability. Leaders who admit their own mistakes, ask for help, and acknowledge what they don't know set a powerful example. Listen actively and invite input. Create space for everyone to contribute. Actively solicit opinions, particularly from quieter members, and respond constructively to every contribution. Frame failures as learning opportunities. After an incident, shift the conversation from "who did this?" to "what can we learn from this?" Protect those who speak up. If someone raises a concern or admits an error, ensure they are met with support, not criticism. Leadership's role: champions of transformation. Cultural transformation never happens from the bottom up alone. It requires explicit support and active participation from senior leadership. Without this commitment, DevOps initiatives often die from a lack of resources, conflicting priorities, or a perceived lack of importance. Effective leaders in a DevOps transformation will provide top-down buy-in, clearly communicate the vision for DevOps, articulate its business value, and demonstrate unwavering commitment. This involves allocating necessary resources, time, money, people, and actively removing organizational obstacles. Lead by example. Managers must embody the desired cultural shifts. If they preach collaboration but operate in silos, the message won't land. If they demand psychological safety but punish mistakes, trust will erode. Empower and grant autonomy. Trust teams to make decisions, experiment, and solve problems. Provide clear boundaries, but allow teams the freedom to choose how they achieve their goals. This fosters a sense of ownership and accountability. Coach, not command. Instead of dictating solutions, leaders should coach their teams, guide them through the change process, and help them discover their own effective ways of working. The practical side. Changing processes to support culture. While culture is abstract, it is reinforced by concrete processes and habits. These practices become the daily rituals that embed the new culture. Formalizing blameless postmortems. Establish a clear process for conducting postmortems after an incident. This includes documenting what happened, the contributing factors, systemic, process, human, the impact, and the specific actions to prevent recurrence. The output should be shared widely. Value stream mapping, a facilitated exercise where teams visually map out their entire software delivery process, identifying all steps, handoffs, and waiting times. This illuminates bottlenecks, waste, and areas where delays occur, providing a shared understanding of the flow and where to apply lean principles. Communities of practice. Encourage cross-team groups focused on specific technical areas, e.g., database management, cloud security, automated testing, or cultural aspects, e.g., incident management, continuous improvement. These communities allow sharing of knowledge, tools, and best practices organically, fostering shared learning. Continuous learning. Dedicate time and resources for ongoing training covering new tools, technologies, and methodologies. This includes ensuring people are cross-trained in areas that traditionally sat outside their primary discipline. Measuring cultural shift. Measuring cultural change isn't as straightforward as counting deployments. However, it's vital to track progress. This can involve qualitative feedback, regular pulse surveys, anonymous feedback channels, and open forums to gauge team morale, inter-team trust, and psychological safety. Observational changes. Noticing improvements in communication patterns, e.g., fewer emails, more direct conversations, faster incident resolution, and an increase in proactive problem-solving. Business outcomes. Ultimately, a healthier culture should translate into improved technical performance metrics, like the DORA metrics discussed in Chapter 8, and positive business results, such as increased innovation or better customer satisfaction. The long game. Cultural transformation is a journey, not a destination. Transforming an organizational culture is arguably the hardest and longest part of a DevOps journey. It requires patience, persistence, and a willingness to commit for the long haul. There will be setbacks, resistance, and moments where it feels like progress is impossible. However, the reward is immense. Happier, more engaged teams who are continuously learning and improving. This leads to higher quality software, faster delivery of value, and ultimately, a more resilient, innovative, and competitive organization. By focusing on people, fostering psychological safety, and enabling learning, organizations can build a DevOps culture that truly thrives. Chapter 11. Common Pitfalls and Success Stories. Real-world lessons. By now, you should have a solid understanding of what DevOps is, its foundational principles, CALMS and the 3 ways, and its core technical and cultural practices. It sounds promising, even revolutionary, as it reshapes how organizations build and operate software. However, like any significant transformation, the path to successful DevOps adoption is rarely smooth. Organizations often stumble, hit roadblocks, and can even fail to realize its full potential. This chapter will highlight some of the most common pitfalls organizations encounter on their DevOps journey. More importantly, it will balance these warnings with inspiring, simplified success stories that demonstrate how various organizations, from agile startups to traditional enterprises, have leveraged DevOps principles to achieve remarkable results. The goal is to provide practical wisdom, helping you navigate your own DevOps journey by learning from both triumphs and tribulations. Common pitfalls, where DevOps transformations go wrong. Understanding what not to do is often as valuable as knowing what to do. Here are some of the most frequent missteps. The tools-first trap. This is perhaps the most common and seductive pitfall. Believing that merely acquiring a set of shiny new DevOps tools, automation servers, monitoring dashboards, container orchestration platforms, is the DevOps transformation. Problem: tools are enablers, not solutions in themselves. Without addressing the underlying cultural, process, and organizational issues, these tools often sit underutilized, are misapplied, or create new forms of complexity and bottlenecks. It's like buying a state-of-the-art kitchen for our restaurant without training the chefs, redesigning the menu, or streamlining the service process. Solution: focus on the why and what before the how. Start with understanding your pain points and desired outcomes. Begin with cultural shifts and process improvements, then select tools that enable and reinforce those changes. Lack of management buy-in or support. Without explicit and sustained commitment from senior leadership, DevOps initiatives are often doomed. Problem: without executive sponsorship, DevOps transformation can be seen as a grassroots techie venture, lacking the necessary resources, cross-departmental authority, and protection from competing priorities. Cultural changes, in particular, require top-down vision and support. Solution: build a compelling business case that articulates the value of DevOps in terms understandable to leadership, e.g., faster time to market, reduced operational costs, improved customer satisfaction. Demonstrate early, small wins to build confidence and momentum. Leadership must actively champion the effort, ignoring the human element culture, forgetting that DevOps is fundamentally about people and their interactions. Problem: focusing exclusively on automation and technology while neglecting the associated fear of change, skill gaps, resistance from siloed departments, and the need for psychological safety. This leads to frustrated employees, high attrition, and a superficial transformation. Solution: prioritize cultural change initiatives, invest heavily in training and upskilling, foster psychological safety, and ensure open, empathetic communication. Remember, culture eats strategy for breakfast. Big bang transformation attempt, trying to change everything at once across the entire organization. Problem: such an approach is overwhelming, disruptive, and carries an extremely high risk of failure. It's difficult to measure progress, isolate successes, or learn from mistakes. Solution: start small. Identify a pilot project or a single, enthusiastic team to begin the transformation. Learn from their experiences, refine the approach, and then incrementally expand to other teams, demonstrating success along the way. This iterative approach allows for continuous learning and adaptation. Metrics without action. Collecting vast amounts of data, as discussed in Chapter 8, but failing to act on the insights. Problem: measurement becomes a pointless bureaucratic exercise if the data collected doesn't drive decisions, improvements, or provide feedback to the teams. Solution: link metrics directly to continuous improvement initiatives. Ensure that teams have the autonomy and capacity to use insights from data to improve their own processes and systems. Celebrate improvements identified and achieved through data. Security as a bolt-on, neglecting the principles of DevSecOps, Chapter 9, and treating security as a separate, late-stage activity. Problem: this reintroduces the bottleneck that DevOps aims to eliminate, creates new risks, and leads to costly remediation of vulnerabilities discovered too late. Solution: shift security left. Integrate automated security testing into CI/CD pipelines, build security champions within development teams, and make security a shared responsibility from the earliest stages of design. Perfectionism over progress. Waiting for the perfect tool, the perfect process, or the perfect organizational structure before taking action. Problem: This often leads to paralysis by analysis, delaying the start of the transformation and preventing valuable learning. DevOps is a journey, not a destination. Solution: embrace continuous improvement. Start with good enough, gather feedback, learn, and iterate. The goal is to make small, incremental improvements over time, not to achieve instant perfection. Inspirational success stories, real-world lessons. Despite the challenges, countless organizations have achieved remarkable transformations by embracing DevOps principles. These simplified case studies illustrate the diverse applications and benefits of a DevOps approach. Case Study 1: the e-commerce powerhouse Etsy, precursor to the modern Agile/DevOps narrative. Challenge: in the mid-2000s, Etsy, a popular online marketplace for handmade goods, faced scaling issues. Their manual deployment process was so slow and painful that they were releasing new code only about once a week. This meant stifled innovation, slow bug fixes, and an inability to respond quickly to market changes. DevOps solution: Etsy became one of the pioneers of continuous deployment. They invested heavily in automation, enabling developers to deploy their own code to production dozens of times a day. They embraced the "you build it, you run it" philosophy, empowering small, autonomous teams to own their services end-to-end. They fostered a culture of experimentation and fast feedback. Key takeaways: empowering small, dedicated teams with autonomy and end-to-end responsibility, coupled with relentless automation of the deployment pipeline, can lead to incredible velocity and innovation. Cultural shift: trusting developers to deploy was as crucial as the technical automation. Outcome: drastically increased deployment frequency, from once a week to 50+ times a day, faster innovation, improved reliability, small changes are less risky, and a reputation as a leader in modern software engineering practices. Case Study 2: the traditional bank ING enterprise transformation. Challenge: as a large, traditional financial institution, ING faced intense competition from agile fintech startups and needed to accelerate its digital transformation while adhering to strict regulatory requirements and managing a vast legacy infrastructure. They grappled with slow delivery cycles, siloed departments, and a complex, monolithic IT landscape. DevOps solution: ING embarked on a massive, company-wide agile and DevOps transformation. They didn't attempt a big bang change. Instead, they started with pilot teams, often called tribes and squads in their model, inspired by Spotify, which were cross-functional, self-organizing groups owning specific product areas. They systematically introduced automation, CI/CD pipelines, and gradually broke down their monolith into microservices. Crucially, they focused heavily on leadership buy-in and cultural change, including training on agile principles, fostering psychological safety, and promoting transparency. Key takeaways: executive sponsorship is non-negotiable for large-scale enterprise transformations. Start small to build proof points and learn, then scale gradually. Embrace regulatory challenges as opportunities to automate compliance. Focus on changing organizational structures and embedding a culture of delivery and continuous improvement. Outcome: significantly reduced time to market for new products and features, improved operational stability, increased employee engagement, and a strengthened competitive position in a highly regulated industry. Case Study 3: the mid-sized SaaS company segment, scaling agility. Challenge: as a rapidly growing software-as-a-service, SaaS company segment struggled with scaling its operations. Their infrastructure was becoming complex, deployments were inconsistent across environments, and new engineers found it difficult to contribute quickly. DevOps solution: segment heavily invested in infrastructure as code, ISC, standardizing their provisioning processes across environments. They built robust, automated CI/CD pipelines for all their services, ensuring consistency and reliability. They also focused on building a blameless culture, learning from incidents, and fostering strong communication between engineering teams. They adopted strong observability practices, giving engineers deep insights into their running systems. Key takeaways: standardize where possible, especially infrastructure. Invest in automated pipelines and comprehensive observability from the start. Focus on developer experience, making it easy for new team members to be productive quickly. Outcome: achieved a highly reliable and scalable platform. Faster onboarding for new engineers, consistent and reliable deployments, and significantly reduced operational overhead. They became known for their engineering excellence and reliability. Your DevOps journey, a call to action. These stories, despite their varied contexts, share common threads: leadership commitment, a focus on automation, a dedication to collaboration, and a relentless pursuit of continuous improvement. There is no single right way to do DevOps, and your organization's journey will be unique. The key is to start. Identify your biggest pain points. Pick a small, motivated team. Implement 1 or 2 DevOps practices that address those pain points. Measure the impact. Learn from your experiences, both successes and failures. Celebrate your wins. Then, armed with that knowledge, iterate and expand. DevOps is not a fixed destination you arrive at. It's an ongoing philosophy, a continuous pursuit of excellence in software delivery. By applying the principles and learning from the experiences of others, you can unlock incredible agility, resilience, and innovation within your own organization. Chapter 12: The Future of Software Delivery, AI, SRE, and Beyond. We've journeyed through the origins, core principles, and foundational practices of DevOps. Understanding how this methodology has transformed software delivery from a chaotic manual process into a highly automated, collaborative, and continuous flow of value. But the world of technology never stands still. Just as DevOps evolved from Agile, new trends and challenges are continuously emerging, pushing the boundaries of how we build and operate software. This final chapter looks ahead, exploring how the core tenets of DevOps will continue to adapt and expand to meet the demands of an ever-accelerating digital landscape. We'll examine the evolving roles within it, the impact of artificial intelligence, and other key trends shaping the future of software delivery. The evolution of operations roles. From admins to site reliability engineers, SRE. As automation and infrastructure as code became prevalent, the traditional role of systems administrator began to evolve. The manual, repetitive tasks that once consumed much of an ops person's day were increasingly automated away. This freed up operations professionals to focus on more complex, engineering-focused challenges, designing resilient systems, automating remediation, and continually optimizing performance. This evolution led to the rise of site reliability engineering, SRE, an approach pioneered at Google. SRE is often described as what happens when you ask a software engineer to design an operations function. While not strictly synonymous, SRE is widely considered an excellent, rigorous implementation of DevOps principles, particularly the second way, feedback, and the third way, continuous learning. Key concepts from SRE that are profoundly influencing the future of operations include service-level objectives, SLOs, and indicators, SLIs. Instead of vague notions of uptime, SRE defines precise measurements, SLIs, e.g., latency, error rate, throughput, and sets clear, agreed-upon targets for those measurements. SLOs, e.g., 99.9% of user requests should complete in under 300 milliseconds. This allows teams to have a shared, objective understanding of the service's reliability and performance. Error budgets. Connected to SLOs, an error budget is the acceptable amount of unreliability for a service. If a service aims for 99.9% availability, it has 0.1% downtime budget to spend. When a team is within its error budget, it can prioritize feature development and experimentation. If it exceeds its error budget, it must shift focus to reliability work. This powerfully aligns engineering and business goals around reliability. Toil minimization. SREs are constantly striving to reduce toil, manual, repetitive, automatable, tactical tasks that don't produce lasting value. Their goal is to automate away as much of this toil as possible, freeing themselves to focus on engineering solutions that improve system reliability and efficiency. Blameless culture. As we discussed in Chapter 10, the SRE practice strongly emphasizes blameless postmortems for any incident. Learning from failures is prioritized over assigning individual blame. The SRE mindset encourages operations engineers to think like developers, using software engineering principles to build resilient, self-healing systems and automate their management. It symbolizes the complete integration of development and operations, transforming once disparate silos into a unified engineering discipline focused on service reliability. AI Ops, artificial intelligence for IT operations. Our modern systems generate an unprecedented volume of data logs from thousands of servers, metrics from millions of data points, traces from complex microservices architectures. While valuable, this deluge of information can overwhelm human operators, making it difficult to identify critical signals from noise, spot emerging patterns, or diagnose problems quickly. This is where AI Ops, artificial intelligence for IT operations, comes in. AI Ops applies artificial intelligence and machine learning techniques to IT operations data to automate and enhance various processes. It's about bringing the power of AI to the measurement and feedback pillars of DevOps. How AI Ops helps: proactive anomaly detection. AI algorithms can analyze vast datasets to identify subtle, unusual patterns that might indicate an impending problem, long before they escalate into outages. Root cause analysis. AI Ops can correlate events across different systems and layers of the infrastructure, helping to pinpoint the underlying cause of an issue much faster than manual investigation. Predictive analytics. By analyzing historical data, AI Ops can forecast future incidents, such as potential resource exhaustion or service degradation, allowing teams to intervene proactively. Noise reduction. AI Ops platforms can intelligently filter out irrelevant alerts and consolidate related alerts, reducing alert fatigue and allowing operators to focus on what truly matters. Automated remediation. In some cases, AI Ops can even trigger automated actions to resolve common problems without human intervention, such as restarting a service or scaling up resources. AI Ops will not replace human operators entirely, but it will fundamentally change their roles. Operators will increasingly become AI whisperers, training, calibrating, and overseeing AI systems that handle the routine heavy lifting, allowing human experts to focus on complex, novel problems and strategic initiatives. Platform engineering, building internal developer platforms. As organizations scale their adoption of DevOps, they often encounter a new challenge: how to provide hundreds or thousands of development teams with consistent, secure, and easy-to-use tooling and infrastructure without repeating efforts or compromising standards. This has led to the rise of platform engineering. Platform engineering is the discipline of designing, building, and maintaining internal developer platforms that enable self-service capabilities for engineering teams. The goal is to provide a curated, golden path for developers to provision infrastructure, deploy applications, access monitoring, and utilize other common services, all wrapped in a delightful developer experience, DevX. Think of it as creating an internal product for developers. This internal platform team simplifies the underlying complexities of cloud infrastructure, security, and compliance, offering developers a streamlined interface. For example, instead of developers directly configuring Kubernetes clusters, they might use a platform portal to deploy a new service with a single click. And the platform team ensures all the underlying infrastructure, networking, and security configurations are handled automatically and correctly. The goals of platform engineering align perfectly with DevOps principles. Increased developer productivity. Developers spend less time on manual infrastructure tasks and more time writing business logic. Consistency and compliance. The platform enforces best practices, security standards, and compliance automatically, reducing human error. Accelerated feature delivery. Developers can quickly provision what they need, leading to faster innovation. Improved developer experience, DevX. Happy developers are productive developers. Platform engineering effectively creates the paved roads for teams to safely and efficiently travel on their DevOps journey, abstracting away unnecessary complexity and allowing application teams to focus on delivering high-quality software to end users. Other emerging trends and the enduring principles. The landscape of software delivery is constantly shifting, with other trends also shaping its future. FinOps, bridging the gap between finance and cloud engineering, ensuring that cloud spending is optimized and aligned with business value. Sustainable software engineering, focusing on minimizing the environmental impact of software and its supporting infrastructure. Increased focus on supply chain security. As software supply chains become more complex, ensuring the security of every link, from open-source libraries to deployment pipelines, is paramount. What remains constant amidst all these technological and methodological shifts are the core, enduring principles of the DevOps revolution. Regardless of the tools or specific practices employed, the spirit of DevOps will continue to guide the best organizations. Collaboration and empathy, breaking down silos and fostering shared understanding across all functions. Automation and continuous improvement, eliminating toil, reducing errors, and constantly seeking better ways to work. Data-driven decisions, using metrics and insights to guide actions and validate outcomes. Learning from experience, embracing experimentation, accepting graceful failure, and cultivating a culture of psychological safety for continuous learning. These principles transcend specific technologies and will continue to be the North Star for high-performing organizations in the digital age. They ensure that software delivery remains agile, resilient, and responsive, enabling businesses to innovate faster, serve customers better, and thrive in an ever-changing world. The journey of DevOps is indeed continuous, a testament to the power of human ingenuity and collaboration in the face of evolving technological challenges.